very close to it. In other words, if it is a double star, or as we say most of the time, binary star, there is an important limit imposed on its expansion. As I already said, each star tries to expand into a red giant. But a star close to another star cannot well do that, because the gravitational attraction of the other star will soon overpower the gravitational attraction of the star on itself, and material will begin to flow from our expanding star to the other star. So in a binary star, stellar evolution is considerably changed, because there is mass transfer, mass exchange between these two components. It can then happen that a star which originally was more massive than its companion will end up as the less massive star, because a considerable part with mass has been transferred to the other star. Such a star is, for example, Algol in the constellation of Perseus.
Associated with binary stars are eruptive stars called novae. The sudden appearance of one of these eruptive stars is signaled by a rapid rise in brightness amounting to tens of thousands of times in a few hours. A slow decline in light may then persist for a year before the star settles down to its former obscurity.
We believe that a nova is actually a binary star with two components very close to each other. One of them is probably a white dwarf. Material flows from the other star to the white dwarf, but the white dwarf has a very peculiar structure. It cannot accommodate the inflowing material very easily. Rather, after a little bit of it has accumulated at the surface of the white dwarf, there is a violent eruption, and the material is thrown into space. And this outburst is observed as the outburst of a new nova star.
The question of how many times a nova can explode is a very interesting one. Before we did some recent work on the Andromeda galaxy, the answer that you would find in a textbook or a discussion of novae, or the answer that would be in most people's thinking, is that a nova, a classical nova, explodes only one time. We have been able to identify a class of dying stars in the center of the nearby Andromeda galaxy. And in the course of a discussion with one of my graduate students, Chris Price, the question came up of whether or not we could be confusing any of the stars that we thought were dying through the planetary nebula stage with novae. And as a result of this question and some consideration of it, I realized that if we compared the number of novae in Andromeda to the rate at which stars were dying, we might be able to say something about the number of times a nova explodes. And the reasoning is fairly straightforward, and it goes like this. Let us suppose, for the moment, that every dying star becomes a nova, and let us then suppose that a nova only explodes once. Then, when I compute the death rate in the central regions of Andromeda, under these assumptions, the nova rate should be exactly equal to the death rate. But suppose now that when I compare the frequency of novae to the rate at which stars are dying, I find that there are 100 times more novae per year than there are dying stars. Then that would say that if every star that dies becomes a nova, it must explode, the nova then must explode 100 times. Well, when I did the comparison, it was immediately evident that the nova rate greatly exceeds the stellar death rate. I can't make a precise estimate of the number of times a nova explodes, because I don't know precisely what fraction of dying stars will be in novae systems. But what I can conclude is that the number of nova explosions will be very large, and that number may be as large as 10,000.
Red giants and white dwarfs, planetary nebulae and novae, and a whole variety of pulsating variable stars, are phases and events which seem to be connected with the last 10% of the lifetimes of stars like the Sun. But the more massive stars also become red giants, and many of them, too, go through phases of variability. But their ultimate fate is much more violent, say, than the lovely, delicate planetary nebulae. And their finish, the finish of the massive stars, is briefer than the long, slow cooling of a white dwarf. A massive star is destroyed almost instantly in a titanic supernova explosion, which leaves behind a superdense and super mysterious neutron star, or perhaps even a black hole. But just because our own sun's passing will be less flamboyant than that of a massive star, it'll be no less catastrophic to the Earth. Even the slow, peaceful end of the sun will destroy us. At least, however, it won't come as a surprise. We can calculate what the sun's future will be, what the past has been for that matter, and we realize that we're about halfway through the main sequence part of the sun's life, that we've got about another 5 billion years before the sun becomes a red giant. When it does so, at the surface it'll become cooler, but it will still be hot enough to vaporize most materials, and the overall brightness of the sun will be greater. And as the sun expands, the oceans will boil, and the air, our atmosphere, will evaporate off into space, and the ground beneath our feet will melt. And altogether, the Earth will not be a very pleasant environment. Well, there was once a lady who approached an astronomer who was giving a talk on the future of the sun, the evolution of stars, and what that means to the Earth. And after the talk was over, she said, "Professor, how long did you say it will be until the sun will destroy the Earth?" And the astronomer answered, 5 billion years. And the lady replied, "Oh, that's a relief. I thought you said 5 million.